In this talk, we present an unsupervised deep homography estimation approach. This work was completed by Nianjin Yi et al. In Megvii Technology. Our code is available at the GitHub link. Simply speaking, the contribution of our method are three folds. First, we propose a new representation called homography flow. Next, we propose a LRR block to reduce rank of features. Finally, a feature identity loss is introduced to stabilize the optimization process. As the GIF shows, there is a moving bus in the unaligned frames. Given the image coordinates, a homography matrix can be converted to a flow map by transforming the image coordinates and minus their original positions. The flow calculated from homography only describes the parallax of the dominant plane, while optical flow depicts every pixel's motion between two frames. The flow from homography only has limited motion representation capability, i.e. low DOF, which means the low rank characteristic. Thus it is possible to introduce flow bases that span a subspace in which the flow lies. Here we propose to construct the flow from homography by assembling 8 pre-computed flow bases. Finally, the constructed flow, we call it homography flow. As homography has only 8 DOFs, the homography flow lies in a low-rank subspace. However, the rank of the motion features through the network are usually much higher than that of a homography. From this observation, we propose a low-rank representation block to decrease the rank of the features by projecting them into their low-rank subspaces. Deep features are usually adopted to achieve robuster estimation. We found that when using triplet loss to learn alignment on deep features, training is often unstable or even the model does not converge. The primary reason is the image feature alignment is not always equal to image alignment. For comparison, here we introduce the two mainstream homography estimation strategies of previous methods. The first one is to directly regress the elements of a homography matrix. It is not optimal as they are with different magnitudes. The second one, i.e. the current solution, is to regress 4 offsets, which is equivalent to a homography if feeds them to the DLT solver. In this work, we start from a new direction by proposing a homography flow representation. Firstly, we need to generate 8 orthogonal flow bases. It is noticed that different image pairs alignment processes share the same pre-computed flow bases. The network is used to estimate different weights to combine flow bases and obtain the homography flow. To obtain the orthogonal flow bases, we first generate 8 homography matrices by modifying each single entry HI of an identity homography matrix, except for the entry at the position of the right bottom corner, which is always normalized to 1. Given the image coordinates, a homography matrix can be converted to a flow map by transforming the image coordinates and minus their original positions. Then, 8 homography flows are normalized by their largest flow magnitude, followed by a QR decomposition. The visualization of all the pre-computed 8 flow bases H1 to H8 are depicted here, and the center is flow legend. Here is our network structure. Given 2 input gray images IA and IB, 2 modules extract the features of them, so that we get the feature maps FA and FB. We concatenate FA and FB and then feed them into a module of homography estimator, which adapts a backbone of ResNet34 with our newly introduced LRR blocks, produces 8 weights that are used to linearly combine 8 pre-computed flow bases to obtain homography flow HAB. If we use equations to express the aforementioned process, we can get the following equations on the slide. Here F and H are the feature extractor and homography estimator respectively. Here is the LRR block that is used to reduce the rank of the motion features. The LRR block consists of shallow residual convolution layers with kernel size of 1 and learns k bases for the input motion feature m in forwarded by the preceding layers. It then generates an output motion feature m out of rank at most k by subspace project. This figure describes accumulated energy of the principal components of the motion features, before and after the first and second LRR blocks. The number of principal components is reduced obviously, which reflecting the rank of the motion feature is highly reduced. On the other hand, the motion outliers are motions caused by dynamic contents or non-planar depth variations outside the solution space of a single homograph, which will be excluded during the rank reduction. Our total loss could be expressed as here, which contains triplet loss, feature identity loss and a regularization term. In practice, we swap IA and IB as data augmentation. We adopt the triplet loss to enable unsupervised training. The original idea on the triplet loss tries to learn a discriminative feature and an accurate homographa simultaneously to well align the input image. Where the homographa estimation is primary target and the auxiliary target is used for avoiding all zero solution. However, the auxiliary item FA-FB may be over-maximized while the primary item FA'-FB is still under-minimized. Specifically, if the trivial direction occurs, though the triplet loss is decreasing, the auxiliary item becomes dominant so that the primary item cannot be optimized normally, and even increases. Conversely, the desired direction presents as that the primary item is decreasing normally and the auxiliary item is increasing simultaneously. To this end, we add feature identity loss to preserve the warp equivariance of the learned feature, meaning that the final feature should be approximately identical if we swap the order of warp operation and feature extraction. With the FIL constraint, the optimization of feature extractor can be stabilized, improving the accuracy of estimated homographa flow. As the figure shows, where without FIL involved, the triplet loss is less than the one optimized with FIL. Even though FA'-FB becomes larger. As a result, the alignment accuracy is downgraded without FIL. We evaluate our method using the same dataset as in Zhang et al.'s, which covers 5 different scenes including regular, low texture, low light, small foreground and large foreground. Firstly, we list all the quantitative evaluations here. There are 3 DNN-based methods and 14 feature-based methods, of which the latter includes 6 manual descriptor methods and 8 deep feature descriptor methods. This table shows the errors where our method achieves the lowest error in average for all the scenes. Even for the regular scene that is friendly to feature-based methods, our results are also competitive. Furthermore, we evaluate the robustness of all the methods by setting thresholds to judge if a homographa matches the marked points. Points with errors lower than the threshold are considered matched inliers, otherwise they are judged as outliers. As seen, our method, the red curve, achieves the highest inlier percentage if the threshold is greater than 0.8. Indicating our method can handle intractable cases better than the others. Then here are some ablation analyses. The third row of table shows the result of Zhang's network adopting homographa flow representation with mask outlier removal and achieving a lower average error. As for the FIL, it further enhances the network performance as shown in the fourth row. When bases and FIL are introduced in our specially designed network which is equipped with LRR, the effective network has been improved more significantly. The table below shows the comparison of point matching errors when feature extractor contains a different number of convolution layers. As seen, from feature extractor containing 0 to 2 layers without FIL involved in the optimization, the mean square error is gradually reduced while the FIL is increased, reflecting the warp equivariance is damaged. If we continue adding layer to 3, the MSE cannot be decreased, showing that the network cannot be consistently optimized, while FIL keeps increasing. If we add FIL to the optimization goal, we can see the MSE is reduced from 0.6 to 0.5 and FIL is decreased significantly from 0.35 to 0.11. This phenomenon reflects that with warp equivariance preserved, the optimization becomes more stable so that a higher performance can be achieved. Now we show some image examples. In the first row, we see that, in the low light scene, only a small portion of the image contains salient regions that enable the feature extraction. Our method shows better robustness benefiting from the pursuit of low-rank features. Similarly, in the second row of images with large areas of sky and ocean, due to the scarcity of effective textures and the interference of wave motion, other DNN methods cannot accurately grasp the available information and cause the images to be incorrectly aligned. For scenes with varying depth planes and scenes containing dynamic objects, DNN methods are easy to fail due to their lack of a reliable outlier rejection mechanism. In contrast, our method utilizes feature identity loss to ensure the warp equivariance of shallow image features and learns low-rank motion features in deep networks, which enables more stable alignment effects in challenging scenarios. We also compare our method with all the aforementioned feature-based solutions. As seen, the foreground fountain occupies a large portion of images, causing the difficulties for outlier rejection methods, such as Ransack and Magsack. In contrast, our method eliminates the interference of foreground motion and aligns the background building successfully. In this example, the distant mountains in the background are almost static while the nearby islands and water surface are dynamic. This is also a challenging low-texture example, where all of the feature-based methods fail to produce satisfying results, due to either the feature extraction or the dynamic waves. In this example, most of the feature-based methods cannot align the foreground people and the background building simultaneously. So in this talk, we have presented a new deep solution for homography estimation, involving 3 new components to improve the performance of previous methods: a new representation called homography flow, a LRR block to reduce rank of features, and a feature identity loss to stabilize the optimization process. Our method achieves the superior performance compared with the state-of-the-art methods. We hope our method could further inspire more works in the research community. Thank you.